Divers are exposed to many dangers when diving in deep waters. Working unprotected in this harsh undersea environment has created a need to develop ways of operating at great depth for extended periods of time. One answer is to provide divers with an atmospheric hard suit with flexible arms. Another is undersea vessel, such as a submersible or bathyscaphe, that can stay deep underwater for days or even months. From the first diving suit designed in 1690 to the remote control vehicle known today as swimming eyeball, we'll review the development of these devices and explore some modern ideas about working under the sea. Join us for Stories of the Sea.
The human body is not equipped to go underwater. Many unpleasant problems can develop if one is exposed to the ocean environment for very long. At sea level, the atmosphere presses down with 14.7 pounds of pressure per square inch on the human body. Underwater, the pressure increases by 1 atmosphere, or 14.7 pounds for every 33 feet down. At 1,000 feet underwater, the body would be subjected to 450 pounds a square inch, or 6 tons of pressure. It would kill any diver foolish enough to dive to such a depth. In deep water, even the air we breathe becomes dangerous. The deeper you go, the more the air in your lungs is compressed. Go deep enough, and the air itself becomes deadly. Violent convulsions afflict the body and cause a swift death. For most of history, man looked at the ocean as a great watery desert where death was never very far away. For centuries, divers have tried to avoid the problems of deep diving, cold, nitrogen narcosis, and the dreaded bends. The ancient Greeks are known to have reached depths of 75 to 100 feet. A Greek vase dating from around 500 BC shows divers about to enter the sea in their search for sponges. One of the earliest histories of man working underwater is in the accounts of the Greek Scylla and his daughter Cyan, who swam beneath the water and cut the anchor cables of the Persian warships of Xerxes in 480 BC. In more modern times, designers and engineers have looked at ways to encapsulate divers against the harsh underwater environment. Englishman John Lethbridge developed a diving suit. Using the elongated wooden barrel design, Lethbridge was lowered face down in the air-filled barrel for half an hour at a time. Looking out through a small 4-inch porthole, his bare arms extending out through leather seals, Lethbridge made dives to 60 feet. Lethbridge dove for sunken treasure and salvaged shipwrecks for more than 15 years. It wasn't until the early part of this century, nearly 200 years after Lethbridge, that aircraft designer Joseph Perez developed the world's first working atmospheric diving suit, also known as an ADS. All earlier designs had suffered from the fact that the deeper the diver descended, the more the water pressure affected the suit's joints, until it became jammed at depths of 200 feet or more. Perez's suit could work in depths up to 500 feet and was used in the salvage work done on the Lusitania during the 1930s. Despite the suit's proven ability, interest in the device faded because there was little need for deep diving at the time. "40 years later, interest in reviving Perez's design led to the development of new ADS prototypes, using modern materials and machining techniques. In 1971, the first new atmosphere diving suit was ready for testing, and commercial work began soon after. To make a deep dive with conventional diving gear would require a team of divers, a large amount of equipment, and possibly the expensive process of saturation diving. Once the job was finished, the diving team would need hours, if not days, to decompress. An operator in a diving suit can make repeated dives in a single day. He does not require backup equipment or crew, and the operator is always warm. The new diving suits are very light, having a body made of aluminum or reinforced plastic. Joints are all movable with manipulators fitted at the end of each arm. The diving suit has set new records for deep diving, cold, and endurance. They are designed to work on the sea bed or on a solid surface, such as a platform. With all the advantages of using the one-atmosphere suit, there are some disadvantages. Despite all the backup safety systems built into the suit, operators have to contend with the isolation, of feeling trapped or alone at great depth. Some experts believe that there is a psychological limit to which a person can dive alone. One answer to this problem is the use of deep diving vehicles with more than one crew member. In 330 BC, according to Aristotle, Alexander the Great had himself lowered into the sea using some sort of vessel with windows. It wasn't until the early 16th century when Cornelius van Drebbel built a submersible in London, known as the first vessel to submerge beneath the waves. 100 years later, David Bushnell built the first operational submarine, called the Turtle. In New York Harbor in 1776, the Turtle attacked the British man-of-war Eagle. Its one occupant cranked the propeller with one hand while he steered with the other. Although the Eagle was only slightly damaged, it was the first time that an undersea vessel attacked a ship, evaded detection, and returned to base. The next great development of submarines came during the American Civil War. The Confederates built 3 submarines. The H.L. Hunley was built from a 4-foot diameter ship's boiler. Propulsion was by a large propeller turned by hand. In February 1864, the Hunley, rigged with a torpedo on its bow, attacked the Union ship Housatonic, blockading Charleston Harbor. Unlike the Turtle's attack 80 years before, both the attacker, Hunley, and the target, the Housatonic, were sunk. By the end of the 19th century, there were a number of submarine prototypes. The biggest factor in their success was the development of the electric motor and storage battery. Today, there are basically 3 different types of underwater vehicles. These are the submarine, the diving bell, and the submersible. Today's nuclear-powered submarines are designed to stay submerged for as long as 3 months at a time. These war machines of the deep have changed surprisingly little in the years since they were first introduced at the end of the 19th century. But submarines are not equipped with windows, and their periscope can only be used above the surface. They also have no way of observing marine life or retrieving any marine samples and sunken equipment. In the past, ocean explorers used surface ships to dredge the ocean floor. Researchers could only guess as to what samples might be brought up to the surface using their long-distance tools. Oceanographers working blind needed a way to improve their sampling methods. What was needed was an underwater vehicle that could recover samples and be used for undersea observation and exploration. The diving bell, or bathysphere, was the first craft built in the United States especially to explore the deepest parts of the ocean. Designed by Captain J.H. Butler in 1930, the bathysphere was 4 feet 9 inches in diameter and cast out of 1 1/4-inch steel. The sphere itself weighed 5,400 pounds. It carried oxygen tanks inside and had 3 viewing ports. In a series of dives in the 1930s, biologist William Beebe and engineer Otis Barton observed marine life at depths greater than anyone had ever seen before. Off the coast of Bermuda on August 15, 1934, the 2 men set a world record by diving to 3,028 feet. The diving bells, suspended by cable from a surface ship, were better for observations by using their small windows, but their movement was limited by their cables connected to surface ships. The solution came with the proposal of releasing the bell from its surface cables and modifying it into a miniature submarine. 20 years after the record-breaking dives of the bathysphere, a Swiss scientist by the name of Auguste Piccard built his own craft and named it the Trieste. The Trieste consisted of a sphere 7 feet in diameter, suspended from a 60-foot hull containing ballast, With only enough power to move about 2 knots an hour, the Trieste was basically an untethered diving bell. After a series of trials, Picard and the Trieste reached a depth of 10,000 feet. In 1954, 2 French officers in the Trieste surpassed his record by reaching 13,365 feet. On January 23, 1960, Jacques Picard, son of Auguste, and Lieutenant Don Walsh flooded the ballast tanks of the Trieste. 5 hours later, they touched down on the bottom of the Pacific Ocean at the world's deepest point, 35,800 feet, or nearly 7 miles beneath the surface. Despite its record-breaking performance, the Trieste was limited to just making observations during its dives. It required huge logistical support, and there was little scientific or commercial applications it could perform. What was needed was a vehicle that could perform simple underwater tasks and could maneuver to recover samples. The work of Auguste and Jacques Picard and their bathyscaphs was the inspiration that soon led to the development of a new class of undersea craft. One of those influenced by the success of bathyscaph was Jacques-Yves Cousteau, who served as safety officer during Picard's first dives in the Trieste. Jacques Cousteau, a retired French naval officer, designed his own version of a diving vehicle, building a highly maneuverable diving saucer. Cousteau designed the first submersible. This little submarine was propelled by jets of water. It could take 2 men down several hundred feet for a few hours and pick up specimens by using a hydraulic claw. The United States Navy had a strong interest in these types of submersibles. Military submarines were already diving to depths that were impossible to reach if a rescue was needed. The fact that a stranded crew would slowly suffocate while rescue ships hovered beyond their reach pushed research in deep-sea vehicles. The United States Navy began a new program of training and development by buying the Trieste from the French and leasing Cousteau's diving saucer. The Navy set up their new deep-sea program near San Diego, California. In April 1963, the U.S. submarine Thresher went down off the coast of Maine in water 1.5 miles deep. A search was organized, and the Trieste was shipped to the scene. After a careful search, the remains of the ship were found scattered on the ocean bottom. The wreckage was surveyed and photographed. A piece of the ship was recovered, which helped determine what had happened to the Thresher. In 1964, the submersible Illuminaut was launched. The all-aluminum vehicle was built with 2 mechanical arms, 4 viewports, and a core sampler. The 51-foot sub was designed to work at depths of 15,000 feet. Also built in 1964 was the Alvin, a 22-foot-long, 17-ton research submersible owned by the Woods Hole Oceanographic Institution. The key design feature of all submersibles is a pressure hull, usually made out of steel. A spherical-shaped hull gives the best strength-to-weight ratio. The Alvin has a pressure hull made of titanium, which provides both strength and lightness. The Illuminaut not only uses an aluminum pressure hull, but it also uses a cylindrical shape instead of spherical. Lead-acid batteries inside the pressure hull of almost all submersibles drive the vessel's controls. Because of weight restrictions, few submersibles can travel more than a few knots an hour. This is because the use of power-to-weight ratio is low. Speed has to be sacrificed in order to keep the weight down. After hull design and power supplies, the next important feature of submersible design is a life support system. Cylinders of oxygen feed into the cabin, and air is circulated by fans. The vessel's pilot monitors his gauges, always watching for any buildup of carbon dioxide. Early in 1966, a U.S. Air Force bomber collided with its refueling tanker over the coast of Spain. The bomber was carrying 4 unarmed hydrogen bombs, which fell to Earth. 3 landed in a field and were quickly recovered. The 4th was nowhere to be found. The Air Force suspected that the missing bomb had landed in the ocean. The area the bomb was believed to have fallen was quickly divided into squares, and a careful search began. The 2 new deep ocean vehicles, the Alvin and the Illuminaut, were brought in and took part in the search. The Alvin played an important part in finding the lost H-bomb. Together with the Illuminaut, they recovered the missing H-bomb after weeks of carefully searching the underwater canyons off the coast of Spain. The biggest reason for using a submersible is to allow scientists, engineers, and others to see things firsthand underwater. During the golden age of submersibles from 1964 to 1969, many companies spent large amounts of money to build diving vehicles. These submersibles were different from submarines in that they required the assistance of surface support vessels. Their sole function was to explore, gather samples, or make observations. Some of these vehicles belonged to the Navy for military purposes. Most belonged to private industry and were used for special deep ocean investigations. Biologists can study creatures in their natural environment. They can study fish and their habits, which is impossible to do above the surface. Geologists can study underwater formations and study features of the sea floor. Manipulators can pick up rock samples and bring them to the surface. In 1968, French scientist Jacques Piccard, son of the inventor of the bathyscaphe, proposed a unique mission to study the Gulf Stream that flows north along the east coast of the United States. The Grumman Aerospace Corporation sponsored the mission and built the vessel. The mission was to drift with the Gulf Stream, gathering information and studying the little understood forces at work in the warm water current. The U.S. Navy provided instruments, surface ships, and scientists to the mission. The vessel itself was to be named the Ben Franklin, after the American scientist who first mapped the Gulf Stream's current. Frank Crosby, a naval oceanographic officer on board the vessel, explained the mission's purpose.
Primarily, what we're interested in is determining to what extent the submersible can be used as a surveying platform. For centuries, we've surveyed from the surface, and we find that we come up with a lot of gaps or holidays in our records, if you will. We've used the submersible to remap areas that we map from the surface, and we find almost an entirely different picture.
The objective of the mission was for 6 men to drift along in the Gulf Stream for 30 days at depths from 500 to 1,500 feet for 1,500 miles. As the Ben Franklin moved with the current, sonar beacons and transponders allowed the submersible to be tracked from the surface. Cameras were used to photograph marine life and geological formations on the sea bottom. Sensors took continual measurements of current speed and direction, temperature, salinity, and depth. On July 16, 1969, the Ben Franklin was towed about 19 miles off the coast of Palm Beach, Florida. Casting off lines, the submersible disappeared beneath the waves and began drifting with the Gulf Stream. Two surface ships followed the submersible, staying in contact by way of a sonar telephone. The naval vessel USNS Lynch also collected surface data, and once the mission was completed, compared its findings with that of the submersible. As the days passed, the crew of the Ben Franklin collected data as they drifted up the coast of the United States. On day 10 of the mission, off the coast of South Carolina, the submersible had to quickly rise as it encountered bottom obstacles thrusting 100 feet from the sea floor. On the 11th day, vertical waves pushed the Ben Franklin off course, and temperatures dropped to 57 degrees, making work difficult for the crew. The Ben Franklin continued its mission, drifting northward at an average speed of 3 knots, 750 feet below the surface. Finally, after 30 days under the sea, the Ben Franklin surfaced on August 14, 1969, 350 miles off the coast of Halifax, Nova Scotia. The Gulf Stream mission was a success. It answered many questions about the Gulf Stream and its depths. Never before had a mission investigated the Gulf Stream in such detail. While today's diving suits, diving bells, and submersibles are unique ways of visiting the undersea world, they also carry a number of risks for operators and observers. Submersibles are very expensive to operate and maintain. A surface ship, which is adapted to handle the craft, uses a special A-frame to lift and lower the submersible into and out of the water. Submersible operations are dependent on good weather. Surface support is a risky operation when the sea is choppy or the currents are strong. Other methods have been developed to find ways to keep people out of the water completely. New machines, which eliminate the human factor entirely, have become more useful. Operated remotely by men aboard a control ship, unmanned underwater vehicles are controlled by propellers on the craft's port and starboard sides, giving these craft great maneuverability. Fitted with video cameras, lights, sonar, and other sensors, these unmanned devices can explore the ocean, extending men's eyes, ears, and hands far into the depths of the sea. Lowered from a ship close to the area it is to work, these remote vehicles are controlled from the surface by a power and signal cable. Unlike divers or manned submersibles, unmanned vehicles remain in continuous operation underwater for extended periods of time, in all kinds of weather, all day and night, without the need to surface. Graham Hawkes is an internationally respected ocean engineer. Since 1970, Hawkes has designed more than 300 remote-operated vehicles for the military and civilian companies worldwide. Hawkes began his own company, Deep Ocean Engineering, with Dr. Sylvia Earle.
Graham Hawkes and I co-founded Deep Ocean Engineering several years ago with the idea of developing equipment for deep ocean access. Deep Ocean Engineering produces a number of underwater vehicles that are operated remotely from the surface. The person who's interested in finding out what's going on under the ocean sits warm and dry on the surface on a deck of a ship, looking at a video screen and flying the underwater portion of the system using joystick controls, rather like a sophisticated video game, really simple to operate. Suppose, for example, you find a shipwreck and you want to scout over the whole length of the ship. You can do that with this vehicle in depths to 1,000 feet.
In 1985, Hawkes designed and built the Deep Rover, a vehicle in which he set a world record of 3,000 feet for diving solo. Deep Rover's development included a revolutionary design in robotic arms.
And so the magic thing about operating this one is that you have the very fine dexterous control that would let us almost dissect an insect, but it has the strength of a crane, it has the power of a bulldozer.
Today, Hawkes is president of Hawkes Ocean Technologies, also known as HOT. In October of 1996, he introduced a new class of underwater vehicle called Deep Flight 1. Deep Flight is a 14-foot, 2,800-pound submersible prototype capable of diving to 3,300 feet. This winged vehicle is highly maneuverable and capable of underwater acrobatics. Hawkes plans to build a more advanced version called Deep Flight 2, designed to go to the deepest point on the Earth, the Mariana Trench. This project is an important step toward accessing the unexplored ocean, where 95% of all life on this planet lives. One of the leaders of ocean exploration is the U.S. Navy's Dr. Bob Ballard. Dr. Ballard is a pioneer in deep ocean technology, having helped develop the Arco-Jason system. The Arco-Jason technology has allowed Dr. Ballard to uncover the watery grave of the German battleship Bismarck, sunk during World War II, and the final resting place of the Titanic, which sank in 1912. These remote robotic systems are able to stay submerged for hundreds of hours and give researchers a valuable new tool to explore the ocean's depths. Although we've been exploring other planets for more than a generation, we have just begun to explore the deep oceans of our world. Much more will ultimately be discovered besides sunken ships. Future generations will be able to make discoveries not yet imagined.
In the 50 years since man began seriously exploring the bottom of the sea, there's been noticeable deterioration of the planet's oceans. Many of the ocean's ecosystems are being destroyed. There is little future for this planet if we willfully turn the seas into a dumping ground. If the ocean is going to continue to help supply us with resources for the future, we need to address a number of problems today. Together we can make a difference. Please help us protect the sea that so many of us know and love. I'm Zan-Misélel Κουστώ, and this is one of many stories of the sea.